Bismillahirrahmanirrahim. So we are back with our third class in the crystal field splitting as far as the octahedral complexes are concerned. तो octahedral complexes में हमने अभी तक 2 classes ली, उसमें basics की कैसे octahedral field या octahedral complex में जो है ये जो है the d orbitals they split into T2g and E set. Now आज इसका last class है octahedral crystal field splitting में. We'll take some examples, a couple of examples. जहां पे हम ये देखेंगे कैसे प्रॉपर्टीज वैरी हो जाती हैं डिपेंडिंग ऑन द विच लिगैंड इज प्रेजेंट इन द कॉम्प्लेक्स एंड हाउ एक्चुअली द इनर ऑर्बिटल एंड आउटर ऑर्बिटल कॉम्प्लेक्स आर फॉर्म्ड. तो आज हम इसको प्रैक्टिकली देखेंगे. विल टेक एग्जांपल्स ऑफ आयरन कॉम्प्लेक्स. विल स्टार्ट. लेट अस से वी हैव अ ट्रांजिशन मेटल आयरन. So let's have its 2 complexes. One is its complex with fluoride, which is a weak field ligand as per as the spectrochemical series is concerned, and we'll take another ligand, strong field ligand, that is cyanide. So its complex is Fe. A बहुत important class है as far as the practical applications is concerned. FeCN whole 6 4 negative. This is one complex. So another complex is FeCN. Sorry, FeF. Octahedral another complex. Fe fluoride 4 negative. तो आप अगर थोड़ा सा इन कॉम्प्लेक्स को देखिए तो सेम कॉम्प्लेक्स है. इस पे भी 4 नेगेटिव चार्ज 4 आयरन सेंटीमेट लाइन. इट्स प्लस 6 fluoride ligand there, but difference is they are weak field ligands as for the spectrochemical series. हमने कहा था वहां पे कि they have the less these ligands, fluoride ligands like fluoride halides and so on, they actually cause the least crystal field splitting. यानी वो जो splitting T2G EG का गैप है ये वाला, इस तरह से हमने splitting दिखाया है T2G EG का octahedral complex में. So extent of this gap, one of the main factors is the type of ligand present. So these are called weak field ligands because they cause this less splitting. Now fluoride is called strong field ligand because they can cause greater splitting. ठीक. Now इस सब को अंडरस्टैंड करने के लिए लेट्स हैव दिस अंडरस्टैंडिंग बाय स्टार्टिंग विथ आवर कॉम्प्लेक्स. दोनों को हम स्टडी कर लेते हैं. नाउ लेट्स टेक द एग्जांपल ऑफ दिस ऑक्सीडेशन स्टेट ऑफ आयरन. हियर इज so X is equivalent. So that's plus 2. So in this case also fluoride का 6 minus cyanide का 6. तो इसमें भी so दोनों में transition metal line जो आयरन है its oxidation state is plus 2. That means initially, since we know atomic number of iron is 26, so now since it is Z2 form, it's iron 2. That means it is we have so it has 24 number of electrons. Okay? So same is the case here. Now it is Z2 system, that is iron 2. So that means your Z is now actually 24 number of electrons. So इसका जो हम electronic configuration बना लेते हैं because now both are same. It has 24 electrons, it has also 24. So in general we should say that iron 2 has electronic configuration. हम पहले वाले नहीं दिखाएंगे इसे. That is D6 4s0 3d6 4p0 and 4d. तो ये इसका जो है आउटर मोस्ट जो उसके ऑर्बिटल्स है ये इसकी पोजीशन है. सो बेसिकली इसमें होता ये जो D6 था इट वाज 3d6 और 4s2. नाउ एज हमने +2 बना लिया तो ये 2 इलेक्ट्रॉन निकल जाएंगी आउटर मोस्ट ऑर्बिटल से 4s से. सो वी हैव 3d6 लेफ्ट. So actually our electronic configurations is, so let us not talk about these because they are not involved in bonding. Their effect is not that much. They are inner orbitals in electrons. So this is 3d6 4s2, 4p6, 3d10. Now, is case may be same. It's present in the same state and it is present in the same state. Now, why actually this is a different properties and this is a different properties. Now, so yahan tak to I have tried to understand the existence of iron, how it exists and what is the electronic configuration now. So we have established it now that in both these complexes we have the electronic configuration as 3d6, 4s2, 4s0, 4p0 and 4d. So outermost shell is 4. So 3d is inner one. So this is your iron 2 in both the complexes. So this is the stats of iron 2. Now let us take the first example. Now in this complex, since cyanide is a stronger field ligand, that means during its complex formation, its approach toward the metal line will lead to the splitting of the d orbitals. Now let us say these are the 5 d orbitals, 1, 2, 3, 4 and 5. So we have a splitting. So this is your T2G and this is your EG. Now this gap, T2G EG gap, which is called as octahedral crystal field splitting or crystal field splitting as stabilizing energy. So this gap is very much larger. Now हमारे पास जो D में 6 electrons है. Now we have to distribute the 6 electrons. So we'll do like this: 1, 2, 3. Now, as per Hund's rule of maximum multiplicity, हम पहले एक इलेक्ट्रॉन रख लेते हैं each orbital में. So as normal procedure is that we'll keep one here, one here. Now if we add electrons here, that means we are supplying this much energy. आपको इतनी energy चाहिए to give to that particular electron so that now it can be placed here. It's here, but this gap is larger. So as per the crystal field theory, this amount of energy is not possible. You cannot get this energy from anywhere. So the result is that electron will sit here. This is your 4th electron. This is your 5th electron. And this is your 6th electron. So rather than the unpaired state, now we have all the 6 electrons. They are paired in the dxy, dyz and dzx. So that means we have 2 orbitals are vacant, dx square minus y square and dz square. So turns out we don't have any unpaired electrons in this complex. That means we know due to the presence of unpaired electrons, the magnetic moment comes into existence. That means no unpaired electron, no magnetic character. So this complex is diamagnetic. So this is a diamagnetic complex. It has no unpaired electrons. Now, as far as this complex formation is concerned, it needs 6 vacant orbitals so as to make the 6 bonds with the ligands. ठीक? 2 इसके पास है. So 2 orbitals के पास available है. They are present from 3D. So आवश्यक है 4. So it will take 1 from here. This will participate these 3 in the bonding. So 3, 4 and 5, 6. So these 3 will participate in the bonding. So it turns out the hybridization will be D2 sp3. Now since inner D, that's 3D, has participated in the bonding, it's called as inner orbital complex. So that is why it's called as inner orbital complex. See? Now no electron is there unpaired. That means it's called as a low spin complex. So it is spin. Unpairing electrons are not there. So it's a low spin complex. Low spin complex. So this low spin complex, inner orbital, this 3D involved the bonding and forming inner orbital complex in the octahedral case. It's all because of the ligand. Cyanide is a stronger field ligand. As per crystal theory, it causes a greater crystal field splitting, and it is not possible to keep the electrons here. Rather, we should say the cyanide forces the electrons to get paired up here. So then these 2 orbitals, they will participate in the bonding, and 1 from S and 3 from pre, so that makes it 6. So we have D2sp3 hybridization, inner orbital complex. So no spin is there, so low spin complex. So this is all about how actually this behaves, iron and hexacyanide complex, the diamagnetic nature and the strong complex, and it's also a highly strong. There's a stable complex. हमने कहा the stability is proportional to this crystal field splitting energy, this one, the gap. Now let's take example number 2, which is iron fluoride. Fluoride is a weak field ligand. That means, so what it will do is, so जो 5 orbitals के पास है, so they will split, but the splitting will be less. उनके बीच में ज़्यादा गैप नहीं होगा, ठीक. So T2G, so this splitting is less, splitting in octahedral complex. When it is less, now we have 6 electrons there. So what we'll do, we'll place there 1, 2, 3. Now चूंकि ये gap बहुत कम है, less energy is required to keep the electron here. So this is feasible, this is possible. It's easy to supply this energy, that's 5. And 6th is automatic here as per Hund's rule of maximum multiplicity. So now that means because of this fluoride ligand, its approach toward the metal complex leads to the crystal field splitting, which is less. We have this situation existing. We have 1, 2. We have 4 unpaired electrons. Okay? So we have 4 unpaired electrons. Now, so as to make the octahedral complex, we need 6 orbitals. Now we don't have vacant orbital here. That is why in this case, this S participates along with this P, and so 1 from here, 1 orbital from here will participate. 3 यहाँ से P से हो गए 4, तो 2 D से participate करेंगे. Since outer D is participating, the hybridization becomes sp3d2. Outer D orbital is participating in the bonding because we don't have a vacant orbital here. Fluoride is a weak field ligand. It is not having the enough power to make the electrons get paired up. So this outer D participates, your sp3d2. It's called as an outer orbital complex. So result is that we have outer orbital complex. Now we have large number of unpaired electrons, so that is, it's a high spin complex. High spin complex. अब जब हमारे पास high spin complex है, that means now we have a lot of spins which are parallel. They will generate the strong magnetic field. So this complex is paramagnetic. So this has a magnetism. So it turns out that is actually the fluoride that creates all this stuff, all these properties, that it makes it outer spin complex, outer orbital complex. Because of less crystal field splitting, it has so many unpaired electrons, number is 4, so it is a large magnetic moment, so it is paramagnetic. So this is the way how actually ligands, they behave as strong field ligands or weak field ligands as per the crystal spectrochemical series, and this is how the property of the complexes changes, even if the metal line was same and the metal line was present in the same oxidation state. तो मुझे लगता है it is enough example. इन 3 parts में हमने divide किया है. Crystal field splitting in the octahedral complex. In the next class, inshallah, hopefully we'll go with the tetrahedral complex, the crystal field splitting in the tetrahedral complex. So this is all